So in this video, I'm going to look at SC23. This topic isn't actually highlighted on your advanced information, but the practical that comes in this topic is. It is highlighted as the core practical that's going to be asked alongside rates of reactions from CC14. So I'm going to run through the core practical that comes up in SC23, and it relates to the combustion of alcohols. So I've written out the formulas of the first four alcohols, and you do need to know these. So the first one I've got here contains one carbon, and it's called methanol. The second one has two carbons, ethanol. The third has three carbons, it's propanol. And the fourth is four carbons, and it's butanol. And you'll see that all of my alcohols have this OH group, because OH is the functional group found in alcohols. And beyond that, as I go from one to the next, all I'm doing is I'm adding one carbon each time, going from C1 to 2, 3, and 4. And each time I add a carbon, I'm also adding two hydrogens, H3, H5, H7, H9. Now you may ask why I've written this hydrogen here at the end instead of including the hydrogen here, so CH4O. CH4O is totally acceptable. The reason I've written it this way is just to highlight the functional group, but if you put this hydrogen with the other hydrogens, that would also be fine. If you're combusting alcohols, you are reacting them with oxygen. So you're burning them in oxygen, they react with oxygen, and they form CO2 and H2O. So exactly the same products as the complete combustion of a hydrocarbon. And it doesn't matter which of these alcohols you burn, you're always going to form CO2 and H2O. The only thing that's going to change is the balancing of your equation will change. And when we're balancing these combustion reactions, the easiest thing to do is balance the carbons first. So here, back in the first equation, I've got one carbon on each side, so that's fine. On this side, I've got 3 plus 1 is 4. So writing the formula in this way does make it slightly trickier to count the number of hydrogens. I've got 4 hydrogens on the left. I need 4 hydrogens on the right, so I'm going to put a big 2 there. And then if I look at my oxygens, I've got 2 from the CO2 and I've got 2 here from the water. So I've got 4 oxygens on the right, and on the left hand side here, you'll see that I have got 3. So what I'm going to do, I don't want to put any number in front of the methanol because that's going to change the carbon and it's going to change the hydrogen, and it's just going to be a bit of a mess. So instead, what I'm going to do is I'm going to put a number here in front of the O2. So if I've got 4 oxygens on this side and I've got 1 here, then I need this to give me 3. So what do I need to multiply by 2 to get 3? And that's going to be 1.5. So 1.5. 1.5 times 2 is 3. 3 and 1 is 4. And then that balances. The next one, I balance carbon first. So I put a 2 in front of the CO2. 5 plus 1 is 6 hydrogens. So I put a 3 here to give me 6 hydrogens. 2 times 2 is 4. 4 and 3 is 7. 7 oxygens on this side. I've got 1 oxygen here, so I need the O2 to give me 6. So I'm going to put a 3. 3 2s are 6 and 1 is 7, and then it's balanced. On this side, C3, so I'm going to put a 3 in front of the CO2. 7 and 1, I've got 8 hydrogens, so I need a 4 here. 4 2s are 8. 8 and 4 is 12. I've got 12 oxygens. I need there to be 12 here. I've got 1 in the alcohol. I need this to be 11. So this is going to be 5.5. 5.5 times 2 is 11 plus 1 gives me the 12 oxygens I need. No, wait. 3, 2, there, 6, 6 and 4 is 10. All right. I need to have 10 oxygens in total. So that, apologies, should be 4.5. 4.5 times 2 is 9 and 1 is 10, and now it's balanced. The next one is going to be the same. 4 carbons on the left, I need 4 on the right. 9 and 1, 10 hydrogens, so I need a 5 there. 4 2s are 8. 8 and 5 is 13. I need 13 oxygens on the left. I've got 1 here, so I need this to be 12. It's going to be a 6O2. So you could be asked to write and balance one of those equations. The other thing you need to know about the combustion of alcohols is that these reactions are always exothermic. So energy is going to be released and the temperature of the surroundings is going to increase. And because they release energy when they are combusted, we can use alcohols as fuels. And some countries do. Some places like South Africa, they use ethanol as a fuel in their cars instead of using petrol and diesel. So we can use alcohols as fuels, and the practical asks you to investigate of those alcohols which is the best fuel. So to see which is the best fuel, what you're going to need to do is do your combustion reaction, and rather than actually lighting the alcohol on fire because they are very flammable, we use what's called a spirit burner. So there would be my alcohol. Let's just say I've got methanol in here. And I light this wick, and the wick is soaked in the alcohol because the alcohol is absorbed on this wick, and if you light it you'll be burning the methanol, but you're burning it in a safe way. And what I do is I need to get the temperature at the start and I need to get the temperature at the end, but I'm not going to get the temperature of the alcohol. Instead, I'm going to place some water above the alcohol, and I'm going to get the temperature of the water instead. So I'm going to place a thermometer into my water. So I've got water there and I've got a thermometer, and to hold that conical flask in place I'm going to use a clamp. So I'm just going to have a little clamp around the neck of my conical flask. And what I would do is I would measure the initial temperature of the water, and let's say I get the water from the tap and it's around 20 degrees Celsius, and then at the end of the experiment, let's just say I'm going to say I want a 40-degree rise, so I'm going to wait until it gets to around 60 degrees Celsius, and then I've had an increase in temperature of 40 degrees Celsius. What I need to do is see, well, how much alcohol did I need to burn to get that 40-degree rise in temperature? So in order to do that, I need to get the initial mass of the methanol. So I'm going to weigh the spirit burner and the methanol, and let's just say the spirit burner and the methanol at the start was 50 grams. And then at the end, after you've completed the experiment and you've had your 40-degree rise, what is my mass going to be now? Well, if I'm burning the alcohol is escaping, it's being converted into carbon dioxide and water, so I'd expect this mass to decrease because the alcohol is being used up. So let's just say at the end I've got a mass of 47 degrees. And what this, 47 grams. So what this tells me is that in order to get my 40-degree increase, right, so I'm going to write here for methanol, in order to get my increase in temperature of 40 degrees Celsius, I needed to burn 3 grams of methanol. And then what I'll do is I'll take ethanol and I'll set it up in exactly the same way. I'll have to use the same mass of water, the same volume of water. So if I used, let's say, 100 centimeters cubed of water in the methanol experiment, I'll need to do the same again in the ethanol experiment, and I'll need to clamp it exactly the same distance above the spirit burner. And what I'll do is I'll do the same. I'll get the initial mass of my ethanol, and I'll get the mass of the spirit burner and the ethanol. And let's just say, again, it starts off as my ethanol is 52 grams, and let's say the final mass of my ethanol is 49.5. And I start again at 20 degrees and I let it rise all the way up to 60. So again, I've had a 40-degree increase, but this time it only took me 2.5 grams of alcohol. So in both, I've got that same rise in temperature, but to achieve that temperature rise, I needed to burn 3 grams of methanol. I only needed to burn 2.5 grams of ethanol. So ethanol is a better fuel. I'm getting it's more efficient. I'm getting the same temperature increase, but I need to burn less fuel. And then let's say you did it with propanol. Well, with propanol, you had a slightly different temperature increase. Just say you ended up increasing the temperature by 42 degrees Celsius instead of by 40. And you worked out the mass of the propanol that you burned, and you saw that you burned 2.6 grams of propanol. And the way I've got this written here, it's just slightly harder to compare. Because I've got more of a temperature increase of propanol, but I've had to burn slightly less fuel, it becomes harder to compare ethanol and propanol. So what you can do is you can do a simple calculation where you take the temperature change, so that would be 40, and you divide it by the mass burned. So I'd have 40 divided by 2.5 for ethanol, and here I'd have 42 divided by 2.6 for propanol. And if you work out, I don't have a calculator, but essentially you'd work out what that, I should be able to do that in my head, and I can't. 40 divided by 2.5, don't judge me. I'm going to get my calculator. 40 divided by 2.5, 16. So that answer there is 16. That's the degree Celsius change that I get per gram. So for every gram of ethanol I burn, I'm going to get a 16 degrees Celsius temperature change. And if I do the same thing for propanol, I'll see that I get, for every gram of propanol that I burn, I get a 16.15 degrees Celsius change. Okay, so propanol again is a better fuel. As I burn 1 gram, I'm getting a greater temperature increase than when I burned 1 gram of ethanol. So if they give you numbers that are harder to compare, you take the temperature change, you divide by the mass, and you'll be able to work out which is the most efficient fuel. Other thing to note here is that heat loss is the main source of error in this experiment, so you need to do whatever you can to minimize heat loss. And what you can do is you can put a draft screen, some insulation around the setup to prevent heat loss. That is your main source of error. I mean, the other thing that they could potentially ask you is they could ask you, instead of working out, you know, your temperature rise per gram, they could ask you your temperature rise per mole. All you would have to do if they did that is, you've got your grams of ethanol, 2.5 grams. You just need to go from grams to moles. So you just use your G Mr. Moles formula triangle. You know you've got 2.5 grams of ethanol. You'd have to work out the formula mass, so it's C2H5OH, so get the mass numbers from your periodic table, work out the formula mass, and then do mass divided by formula mass equals moles. So all you would need to do to convert this to temperature rise per mole is just convert from mass to moles by dividing by MR. I have gone through this in more detail in the core practical booklet. There's loads of practice questions. Please do have a look at it and make sure you are comfortable with alcohols, the structure of alcohols, and these combustion equations, as well as the actual details of the core practicals.